This is the main topic, IR and Raman active mode. So before we will proceed for the calculation of IR and Raman active mode, we should understand how our character table looks like. I'm pretty sure that you might be knowing, but still I want to rebrush some fact. So this is the character table of C2V point group. Okay, so if you see on the left corner, the red circle one, this one. So basically this is called point group. Okay, next this is called symmetry operation. So here four symmetry operation. One is E, C2, sigma xz and sigma yz. And the H is correspond to the order of group. And what is the order of group? It is basically the sum of the coefficient of symmetry operations. So here, how many E are present? 1. How many C2? 1. How many sigma xz? 1. So how many sigma yz? 1. So total order of the group is 4. Right? In the left corner, if you will see here, it is represented as A1, A2, B1, B2. In few of the book, it is represented as tau 1, tau 2, tau 3, tau 4. It is called as irreducible representation. Okay, but here this A1, A2, B1, B2, actually the representation of irreducible prospect can also be written in the form of Mulliken symbol. So it was the Mulliken who has given some rule to write the mode, irreducible representation with respect to the principal axis and also with respect to the mirror plane. Okay, we will learn later. I told you it is A1, right? So A1 correspond to what? That what is the role of mirror plane? If it is symmetrical, then it will be 1. If it is -1, it will be called as B2. So like this way we used to classify it. So this is whole Mulliken representation has been given, where we can use it, what terms and how we can proceed. Now, okay, before starting the Raman and active mode, we should know what is IR active and what is Raman active. So what is IR active? If the molecule is having the change in dipole moment, then it will be IR active. However, if the molecule is having change in polarizability, then it will be called as Raman active. Is that clear? Okay. Now, what is polarization? Okay, in general sense, I can say what is polarizability. So basically, polarizability is the measurement with which magnitude you can distort the electron cloud around the molecule. That will be called as polarizability, right? Okay, so this is a formula to calculate the number of vibrational mode, that is 3n minus 6 and 3n minus 5. 3n minus 5 will be used for linear molecule and 3n minus 6 will be used for non-linear molecule. Okay, now we will learn these many things later. Okay, this is the rule for the representation of molecule before to calculate IR and Raman active. Okay, always remember point 2, the coordinates are assigned according to the convention that the highest fold axis of rotation. Means the principal axis is always aligned along the z axis and the x axis is perpendicular to the plane of molecule. Okay, so suppose the plane is defined with yz, then the x orientation will be perpendicular to the yz. See, about this point I must say the fixed criteria is the principal axis will always follow the z axis, right? For rest of the thing, it all depends that which things you are going to follow. Like from our childhood, what we have learned that x, this is x, now this is y. But always remember, x can be changed, right? But z cannot be. Okay, now see, I will show you from example, right? This is a characters table of C2V point group. Now see here water molecule, right? What the rotation, what the way we have taken, if you will see, it is y-axis, this is z-axis, and this is x-axis, right? Okay, now what we will do, we will bifurcate all the possible atom into the 3 axes. So how many number of atoms are present? 2 hydrogen and 1 oxygen. So the total number of atom present is 3. So you can directly calculate the number of vibrational mode present in the water molecule. If you will see, the formula will be 3n minus 6, n correspond to the number of atoms. So here we will put it 3 minus 6 is equal to 3. So total active, a normal active vibration mode will be 3. Active or non-active we will see later. Now see, we will find out the reducible representation for water molecules. So first our work is to define the axis of all the atom, right? And during this defining, one has to remember that z axis should always accompany the C2 axis or the principal axis, right? And this y can be x and x can be y. It can be acceptable. It all depends that which prospect you are going to apply. So sometime if you will go through with the Cotton, right, he used to opt y as a x and x as a y. But if you will go with Carter or what you call John Bishop, they will follow the same trend what I have mentioned shown here. Okay, so now what we'll do with respect to the symmetry element, we will operate the molecule, and there is a rule that if there will be a change, yeah, the molecule atom is going to move during the operation, then it will be 0, right? And if only the direction is going to be changed, then we will prefer -1. And if it is going to remain unchanged, then we will consider it as 1 for every axis. Okay, for the calculation of reducible repellent. Let us start with E. So what is E basically? E symmetry element में क्या करते हैं? We used to rotate the molecule with 360 degree, right? So anything which is going to rotate it with 360, what you will get? You will get the same thing, right? So I can say that with respect to x, y, z of every atom, nothing is going to be changed, right? So the total number of axes which are going to be unchanged will be 9, right? For oxygen 1, 2, 3. For this hydrogen 4, 5, 6. For this hydrogen 7, 8, 9. So the reducible representation, if you write with respect to E, will be fine. Now let us move towards the C2. Now once you will perform C2 along this z axis, what would be happen first? You will see this H, this one is going to shuffle here, and this one is going to be sit here. So both H are going to be changed. So the contribution will be 0. The only thing which is going to be remain unchanged with respect to atom is oxygen. Now we'll come to the axis. Now see, if you will rotate, what would be happen? Rotate along this C2, what would be happen? This Y is going to be here. This X is going to be here. But Z is going to be remain same. So Z will contribute how much? 1. This X will contribute -1, and this minus Y axis will contribute -1. So total how much it will be? -1, -1, +1. So overall it will become -1. C2 contribution will be -1. Now let us do for ZX. What is ZX? So in case of ZX, if you will see, the plane which should be passed through what? XZ means which is passed through oxygen atom, right? In that case, what would be the scenario? If you will see here, what would be happen? Which are the things are not going to be changed? So see, first of all, if you will pass through the plane through oxygen atom, H again going to be here, this H is going to be here. Is that right? Agreed or not? So in that case, what would be happen? Again, the whole atom is going to be changed. So the contribution will be 0 from both the hydrogen. The only thing which is going to be considered is with respect to the oxygen. In that case, if you will see here, the things which are along the X and Z, they cannot be changed because that is the plane which is going to be considered, right? So the X is going to be remain same, so it is +1. Z is going to be remain same, so again it will be +1. So the contribution will be +2. But what about Y? Y is going to be changed. That will be -Y, I can say. So it will contribute -1. So the overall character will be +1. Now the last is sigma y-z. What is sigma y-z? Sigma y-z is the plane which contains whole molecule, right? The whole molecule. If you look at the whole molecule is going to be considered, in that case, what will be the scenario? It will be 3. How come? Can anybody tell me? Now see, In that case, how come it will be 3? See, again, you always remember, here yz is there, right? So how many number of atoms? 3, right? So yz is not going to be changed, right? So 3 multiplied by 2, so 6 x's are not going to be changed. What axis is going to be changed is x. And how many atom is there? 3. So 3 multiplied by -1, so it will be -3. So the overall for the molecule, it will be 6 minus 3, so it will be 3. So this is the reducible representation. That is, with respect to the E, it will be 9. With respect to the C2, it is -1, sigma xz 1 and 3. So this is the formula for the reducible representation, right? N is equal to 1 by h summation of chi rx multiplied by chi ix dot nx, right? It's quite difficult to understand, but once you will start performing the reducible representation, you will come across. I have mentioned here for your consideration that what exactly it is. For example, what n correspond to the number of operation. What is xy? It is a character of irreducible representation, and x, it is a character of our reducible representation. So this is the character of reducible representation, but these are the character of irreducible representation, right? And 1 by h is the order of class, right? We will do it. Okay, now see here, this is a1, so I have written a1. 1 by h, what is the order of class? The group. So how many E? 1 1 1 1. So h will be 1 by 4. Is that fine? Now 9 is the reducible representation, this one, right? Multiplied by 1, this is 1, then 1 and then 1. For this one it is 3, right? Then 1 and then 1, right? So total we will calculate, it will be 3. Now we will do it the same thing for the A2. So in that case, if you will see for the A2, if you will see, it will become 1, right? Like how it is same way, 1 by 4 irreducible representation 9, then 1, then 1, then again -1 1 1, then 1 -1 1, then 3 -1 and 1. So the overall it will be 1. Like this V1, it will be 2 and 3. So what we can write it, the overall total reducible representation will be 3A1 A2 2B1 plus 3B2. Is that fine? Now, so now tau total is 3A1 plus A2 plus 2B1 plus 3B2. Now translational, always remember the things which are written parallel to XYZ. Yeah, they will correspond to the translational. So if you will see here where the X is written for the B1, right? So what we will write B1, for Y it is B2, and then Z A1. So what we'll write A1, B1 and B2. Now for the rotational, what we'll see R, as I have already told you, right? So RZ kahan likha hai? This is A2, then RY B1 and then B2. So this will correspond to the rotational. Now what we are supposed to find out? We are supposed to find out the vibrational, right? So vibrational, how do we calculate? Vibrational is equal to total mode minus translational minus rotational. So if you see vibrations we are showing here, this is 2 and this is 1, so 2, and this is the spectra I have shown you here, simplified prospect, right? 3 peaks are there.
Anti-symmetric with respect to that principal rotation axis. So notice we have this lopsidedness. So if we did a C2 rotation, the vector that's stretching out would be compressed on the other side and vice versa. So this is lopsided stretching nature. And this B2, this anti-symmetric stretch, occurs at 3,756 wave numbers. And then the next vibration mode that we have is an A1. And this is an A1 stretch. So this is a stretching mode, and this occurs at 3,657 wave numbers. So this is a symmetric stretch. So if we did a rotation about the C2 axis, the extended one also looks like the extended one on the other side, and if it's compressed on this side, it's also compressed on the other side. So it's symmetric with respect to that rotational axis. And then our other A1, because we said, remember, there are three vibrational modes, a B2 and A1, and another A1. This other A1 comes at a lower frequency at 1595, and this is a bend. So this bend produces a change in polarizability and the change in the net dipole moment of the molecule. So once the irreducible anti
Now, using the group theory to determine I have already told you that XYZ for the irreducible representation, then the mode will be IR. Now, so what we have come across is that the total active IR active modes are 2A1 plus B2. Is that okay? Now see, here this is a shortcut I have framed you. Rather than to distinguish all the atom in three bond axis vector, what we can do, we can see the molecule with respect to the atom. Means earlier what we used to, we will rotate along the axis, then we will say how many axes are going to be changed, right? But what we can do, we can see with respect to the atom. Means like if you are operating the oxygen C2, right? So what it is going to be changed, what is going to be remain unchanged? Oxygen is going to be remain unchanged. So what we will say, unshifted atom is 1, right? Unshifted atom for E, all three is going to be. So rather than to distinguish with respect to the axis, what we will do, we will classify it with respect to the atom. So in that case, what we are, additional factor is going to become, that is contribution per atom. For that there is a formula I have already given you. For E you will always write 3, right? For Cn, actually I have already solved it with respect to C2, C3, C4, C6. Otherwise, to find out this, we have a formula 1 plus 2 cos 360 upon, for example, if you want to solve with respect to 180, yeah, C2. So what you will do, n is equal to 2, so cos 80, cos 80 is equal to what? Minus 1. So minus 1 multiplied by 2. So minus 2 plus 1, that is minus 1. So this way. For Sn, this one. So what we will do, contribution per atom is 3 minus 1, 1, 1. And then reducible representation will come. We will multiply this. 3 multiplied by 3, 9, minus 1, 1, 3. But rest of the practice will be same. Like we have to see X, Y, Z axis where it is present. We will write it, and that will correspond to translational, right? And then we'll say Rx, Ry, Rz, that will correspond to rotational. Now you will add translational and rotational and subtract with the total, and you will come across with the vibrational mode, right? The same thing you have done with respect to the axis also. I want to tell you both things are right, right? The only thing is, for H2O the number of atoms is 3, but if you will move towards some complicated molecule, in that case what the problem is going to become, it is very difficult to distinguish all the atom with respect to axis. Like suppose I would say the example CS2Br2, right? CS2Br2 number of atom is 5, every atom is bifurcated in 3 axes, so the number of axis what you have to notify is 20, sorry, 15, right? So it is very difficult. So in that case, what we will do, we will consider this formula, and with respect to that we will find out the reducible representations. So today we have deal with C2V point group, right? As a homework, you have to do for C3V, and then we will move towards some more complicated point group, and we will conclude what exactly